So we have talk of Vassily Manturov about picture-valued invariant.
Thank you very much. I would like to express my gratitude to the organizers of the laboratory and these conferences, Vladimir Georgievich, Sergei Vladimirovich, and Evgenia Anatolievich for the opportunity to be here and to participate and to listen to all those talks and to give a talk. Today I'm going to talk about some pictorial picture-valued, maybe pictures invariants, groups which I call G and K, which are closely related to free groups, braid groups, and some other groups, and various methods of version law theory which turn out to work in classical braids. Here is the outline of my talks. So first of all, I'm going to talk a little bit about trisecants, how one can get crossings not from projecting knots to the plane, but for looking at horizontal trisecants, and how to get groups, which I call G and K, and then how to get invariants of various topological objects, not only links or tangles or whatever, but also actually for many objects and many groups which come from some general position arguments. When we have some right codimension, in many cases we can find an appropriate n and k and get some invariants valued in n and k. So then I will talk a little bit about categorifications and the real meaning of categorification. And also I will talk about some explicit calculations and some explicit applications of what I have done for the case of braids, for crossing number, for unknotting number, for the number of trisecants, and other applications. It will be something from my joint work with Igor Nikonov. And then I will just list applications of the main theorem. And finally, I will talk about what to do with arbitrary tangles, not braids. When we have strands which go not necessarily downwards, but can go up. So, first of all, when we deal with classical Reidemeister knot theory, we have plane diagrams, and actually one mostly considered Reidemeister knot theory in the sense that we have plane diagrams and we are looking for invariants under these plane diagrams. And here, whenever we look at the Reidemeister moves, we always look at crossings. And crossing is the building brick of our knot, and when we, for example, want to have some quantum invariants and so on, we always look at crossing. But if I want to decorate my crossing with some meaningful information, usually I fail because, well, if I want to have a number at the crossing, well, which number can I get? For example, if I color my knot with, say, some quantum coloring, it will change drastically when I do the third Reidemeister move, like here. For example, this crossing or this crossing. But if I want to do some, for example, quantum co-cycle invariants, this will be not an invariant of a particular crossing. This will be an invariant of the knot itself as a certain sum, but crossings themselves will not be invariant. For example, here I wanted just to demonstrate, if you want to, at this crossing, if you want to put the linking number, for example, of a part of the knot here with the rest of the knot, then this linking number changes by 1 if we perform the third Reidemeister move. So here I use the red color for one part of the knot and white is the rest. And if something changes by 1, there's probably no hope to get anything meaningful. So if I want to decorate crossings, possibly crossings are not the best thing we can think about. And that's why I want to look at trisecants, horizontal trisecants, and I will construct a new theory of classical braids with invariants which are varied pictures and free products of the group Z2 with itself. So the key idea in the simplest case is to consider braids as we usually do. We consider braids as motions of points on the plane, a collection of n distinct points, and I will mark some moments when I have a horizontal trisecant. So in the end of my talk, I will give a list of references. So here I refer to a paper which appeared in January on the archive with the corresponding title. So I'm now going to define my groups, which I will call G and K. And the notation of G and K originates from the number of from combinatorics, and in some sense they will be a sort of categorification of the number of combinations of K elements taken from the list of n given elements, and then we will prove the main theorem. So here I'm going to define this group, and this group will have choose n k generators, which will be indexed by m, where m runs the set of all unordered k tuples m1 and k. Modulo 3 types of relations. The relations are coming, and here they are. So first of all, the first relation is a sort of generalization of the Yang-Baxter relation. So in some sense, the usual Yang-Baxter equation we have is something which will be related to Gn2. And now I have, I take some set of k plus 1 elements, and I take all subsets of cardinality k, and I take the product in arbitrary order, and I just write down the relation that this product is equal to the product of the opposite order. That's the first set of my relations. So the second set of my relation is just the Farr commutativity, very similar to the braid group Farr commutativity, when we have two indices.
Sorry, Vassily. M is a set, so your generator depends on a set.
Yeah, so M is a tuple, right? So M is a tuple, and one, and so on, mk. And AM and AM prime commute if these sets have a small intersection. Small means less than k minus 1. So, for example, if k equals 3, then I can have 3-point sets, and their intersection can be 1, but not 2. So this is my form of commutativity, and just to make life easier, I add this relation. Possibly I may do without, but I will add. That's okay. So now I want to say that these groups have many nice mappings. Many nice mappings which are actually something like strand forgetting and strand deleting mappings. So we can, in a way similar to what was done in the previous talk when we were looking at braids and Brownian braids, well, we can remove one strand. And if we remove one strand, we get an obvious homomorphism from the group Gn to the group Gn minus 1k, right? On the other hand, we can not remove, but on the other hand, but do the opposite. We keep the nth strand and take only those tuples which do have this nth strand. So we have J and K, and it's homomorphism to Gn minus 1, K minus 1. And actually, as we write in Russian notation, C and K is equal to the sum, and as it is known elsewhere, choose and K is equal to this sum, and in some sense my groups will be group theoretic analogs, maybe sort of categorification of this simplest combinatorial relations we know. Okay. now, dynamical systems of points in R2. Well, as usual, we want to look at a braid, an n-strand braid, as a motion of a collection of n points. And when we have these n points, we mark all those positions when some 3 of them are on the same line. If some 3 of them on the same line, we note that I always enumerate my points globally. So I don't have local number of strands as we do in the case of usual arting generators, but here I just enumerate them globally, and if 3 of them appear to be on the same line, I just write this generator, AIJK. And then if my braid is in the general position, I read it from the top to the bottom and mark all those points by generators. And I will get a word, and certainly the definitions of my relations in the group G and K were taken in such a way that this group, this word would be an invariant. And actually, of course, we should take into account some non-degeneracy conditions on critical values, for example, that our triple points are non-degenerate, etc., etc. More precisely, what can happen if we have a generic braid? We can have finitely many moments with horizontal trisecants, but no more than trisecants. But if we have an isotopy between 2 braids, what can happen? For an isotopy, we can get some moments with quadrisecants in general position. Finitely many moments with quadrisecants. But also, it may happen that 2 different horizontal trisecants appear at the same moment, simultaneously. These 2 trisecants can be, for example, 1, 2, 3, and 1, 4, 5. They can share a point, but not 2 points. So we can have the situation when 1 belongs to 2 trisecants simultaneously. And this is also a coordination. This also relates to the respective coordination. And also it may happen that, oh, excuse me, I meant the trajectory of zk has a tangency point with the line passing through zi, zj. Let me draw it on the blackboard. For example, if I have, for example, a point 1 and 2, and assume for simplicity that they that they remain untouched, and the point 3 goes like this. So this is the point. This is my 3rd point, and here is the trace of this point. So if I have a dynamical system where this 3rd point does not touch at all, then we will have no generators at all. If I have a situation when it goes like this, then I will have 2 generators written down twice. And actually, these will be 2 coincident generators. They will be A123, A123. And the intermediate moment is exactly the tangent point. So this is exactly the right codimensional, similar to the horizontal quadrisecant and 2 different horizontal trisecants. So from codimension argument, it follows that we have exactly the relations we get. And actually, here is the main theorem. So I formulate it in several terms by using some words, say stable, proper, correct, and whatever. But actually, all those words mean something which means a general position argument. For example, if we have 3 points, if we have points on the plane, it may happen that 3 of them are on the line, but no 4 of them are on the line if we are considering just a braid. But if we consider an isotopy, it may happen that we have some 4 points during during the isotopy. And actually, all those words, I will tell something about them rather than defining it explicitly. Everything is written in the paper on the archive. I will comment on them for this explicit case, and then some other cases and some other examples will come, and we will see what's happening with them.
I'm sorry, did you give a definition of Rope dynamics?
So we have a set of particles.
No, I'm asking, did you give the definition?
No.
But then what you are explaining now?
Now I'm explaining what it will mean in this particular case of endpoints on the plane. So I will explain that this is some general position situation. Then we will. So these definitions are a little bit technical. For example, at some point I will need some some partial derivatives are not equal to each other and so on. So there is some technicality, but here everything mostly means that we have some general position conditions. So here, particles are points on the plane. There are exactly n of them, and the number of particles remain the same. Points are distinct. Well, in general, it may happen that particles for that theorem are not just points. They may be topological objects of any nature. Now, property P means collinearity. And for my case, we have 2 points which are always collinear. 2 points are always connected by a straight line, but 3 points are connected by a line on the same straight line in the case of codimension 1. So this is my property P, and K here is 3. Correctness means that there are, in general position, there are finitely many moments with exactly 3 points which are collinear, but not more, but not 4 points. Stability, so in the previous slide I said something about stable proper dynamics, actually means that my initial braid is not like this. So, when I touch it a little bit, the word will be the same. For example, here, the break is not stable because this tangency point can be resolved in either direction, and in one direction it will be just 1, 2, 3 squared, and in the other direction it will be nothing. So this is not a stable break, and I don't want to write down a word from a non-stable dynamics. So for this it will be nothing. For this it will be 1, 2, 3 squared. So and actually also general position break isotopy means that there are finitely many moments with non-degeneral horizontal quadriseconds or 2 triseconds which happen at the same moment, or a tangency point. So here it's the general position. And actually, if I wanted to be as rigorous as possible, I would also have to say that my quadriseconds should all be non-degenerate, and which quadrisecond should be non-degenerate. Well, it will come in appropriate time, but still it's a bit technical. Now, I want to say several words about what people are usually doing in topology and which invariants we're usually calculating. Well, in fact, most of the invariants we're dealing with are some instances of the number conservation law. We take some pluses and minuses and we collect them together, and then we prove that some a certain sum of +1 and -1 is invariant. the linking number, the mapping degree, the Euler characteristic, the homological intersection, and many other things can be expressed as a certain sum of something with signs. Then, if we are lucky, we may try to get something more elaborated with coefficients, say polynomial coefficients. But this is still a certain number conservation law. And number conservation law, I would say that this is the formula 1 minus 1 equals 0. And I would like to have more complicated objects, and for me, there are first of all homotopy groups or braid groups or some other things, and I want to have a sort of picture conservation law. What do I mean by that? So, well, assume I want to get some nice information from classical knot or braid diagrams. I want to mark crossings somehow and to put some information of topological nature, which encodes something meaningful about the knot itself. About the knot itself, about the link itself. But how can I do it? Well, possibly the very first instance you know is the linking number between two components when I have, for example, a blue one and a white one, and then I can say, okay, there are crossings which are mixed, which have different colors, and there are crossings which are pure, which have the same color, and then we count this somehow with certain signs, and then we have some number conservation law, which gives us the linking number. But can we do something more elaborate for knots? Actually, when we work with usual diagrams, with usual randomized knot theory, then particular crossings do not possess anything interesting. Unless we take a certain sum, unless we take some, say, co-cycles, or unless they are already in some structures. But in virtual knot theory, for example, crossings themselves possess a very powerful information, some homotopy type and so on. And also, there are many instances, say, brackets and co-brackets of curves and surfaces, Goldman bracket and Turaev co-bracket. When we take a certain sum over crossings, but for example, for a knot, we can get a sum of two component links. So every crossing possesses an information which is itself topological, which is itself not a number, but something more powerful. And I want to have a sort of picture conservation law. I want to have a formula when some similar pictures get cancelled, but different pictures do not get cancelled. And then it will be more than just homology, and in some sense, homotopy is more complicated than homology because we have such phenomenon of different pictures which cannot cancel. So this is the simplest instance where we have 1 minus 1 equals 0, where we just want to count some intersection number. Or 1 plus 1 equals 0, I like Z2 more than Z. For me, integral coefficients do not matter, but pictures do matter. And so, for example, if we have something on a 2 surface, we can draw a picture, and if two crossings can be cancelled by a Reidemeister move, then these two crossings are similar in some sense. In which sense? For example, we can resolve these crossings if we have a knot, for example, like this. Then there is a smoothing which transforms a knot to a link. So this is the smoothing here, and we have a two-component link, or two curves on a 2 surface, and we have two homotopy classes. Here are these classes for this crossing. And if I do something for this crossing, those will be the same classes, because from this crossing, well, I will just add a small loop, and homotopy classes will be the same. So in some sense, pictures living at these crossings should be the same. Otherwise, they cannot be cancelled. But how can I get these pictures? How can I get this additional homotopy type information? If I live on a surface with a non-trivial fundamental group, that's okay, I can get it immediately. But if I have just classical braids, I will tell about that.
What is the meaning that here you have two cats, not two dogs?
The meaning that I have two cats, but not a cat and a dog. The meaning that they are the same, that they are equal to each other. Otherwise, they cannot be cancelled.
I do not understand the meaning of the sketch. What is holomorphic bygone?
Holomorphic bygone. Well, you know, many people, when they look at a second Reidemeister move, they can say, okay, these two crossings can be cancelled because they have the same holotopical information. These two chains in the Havana for Auschwitz-Saba complex can be cancelled by a differential because they have the same gradient. These two chains in some other complex can be spanned by a holomorphic bygone because they have the same topological, homotopical, or other gradient information. So many people will see different things when they look at the second Reidemeister move. And this number conservation law, 1 minus 1 equals 0, will have different meaning depending on the information. So for example, if we have this picture, so here I drew on purpose that we don't have a bygone, but we just have two crossings. If we have two crossings but do not have a bygone, these two crossings can be really different. You see, and these two pictures are different. And if someone comes here and stays in front of this picture, he can see these two crossings as something different. As something different. This picture, no, it's mine. It's mine. I can show it in my file afterwards. Okay. So now, one more principle which works very nicely in virtual knot theory, and which hasn't yet been found to work so far in classical knot theory. The principle, which sounds as follows: if a diagram is complicated enough, then it reproduces itself. This means the following: assume we have a complicated diagram. Assume we want to apply Reidemeister moves to increase this diagram. It's impossible for us to decrease this diagram in 1/3. For example, we cannot apply the second Reidemeister move. Then it's possible that we increase it first. If we increase it first like this, we do the increase in second Reidemeister move. We get these two additional crossings. But in this particular example, if we do only one step upwards, then we can see the initial diagram, which is identical with this one, inside this more complicated one, just by using one smoothing. So from this to that, we can get by one smoothing. One smoothing means a smoothing like in the smoothing of the Kaufman bracket. But this is just something we can do in one step. So if everybody knows that if we use just diagrams on the plane, not grid diagrams, but usual diagrams on the plane, it may happen that for that different knots have many different minimal diagrams, and in order to simplify a diagram, we have to go up many times and then to go down. So generally, globally, this principle doesn't work in the classical knot theory. So there is no monotonous simplification if we work with diagrams which are just planar, which when we do with Reidemeister moves. But in many situations in virtual knot theory, this does happen. This does happen And now I want to say a couple of words about the categorification. So what do we usually do to categorify some object, to categorify some polynomial? Instead of numbers, we want to get linear spaces, or maybe something more elaborated, linear spaces with some action or something else. But in order to get some not homology or quantum invariance or whatever, one usually does as follows. One takes some axioms of Hopf algebra, twisted algebra, Frobenius, TQFT, lots of axioms, writes several pages of definitions, and checks whether they work and whether they are consistent, and we can do something. But in my sense, categorification, as my friend Luke Altman mentioned to me, is a way of drawing cats at crossing. So we use a categorification, which means that at every crossing we put some structure. We put some structure, and we don't want to prove that it's a monoidal, it's Hopf or Frobenius or whatever else category. We just want to have a picture itself. But if we have a picture itself, well, we can have some funny group action on this picture. This picture can have symmetries. This picture can have many other things. That was the way how one can enhance Kaufman-Breguet, Havana homology, and whatever else invariance in virtual knot theory by plugging in pictures at crossings, by plugging in many information like this. And now I actually want to associate cats with generators of groups. I want to consider one more toy model, and actually when we deal with free groups or even free products of some finite groups, of some abelian groups, the situation is very easy. The word problem and the conjugacy problem are straightforward. We just look at the minimal representative. So consider this word. This word is minimal in that group. Why? Well, because there are no adjacent letters which can be cancelled. So if we...
Minimal, you mean reduced?
Yeah, it's irreducible. But if we look at some other word representing the same element, it should contain the initial word inside it. So in some sense, it's similar to the picture I drew before. We had a knot diagram, and we did some increasing move, and then we saw the initial diagram inside. Of course, this is a toy model. But if we have a way to get maps from something to, say, free groups, then this will be a way of getting some funny estimates or funny invariants which are valued in something more than just numbers.
What do you mean by inside? It is not inside.
Well, inside I mean that if I just remove several letters, I will get the initial word. So we have two words, and one can be obtained from the other by deleting several letters. Of course, this gives very obvious estimates and very obvious complexity and many other things. For free groups, everything is obvious. Now, I want to consider the case of GN2 braids. And actually, these GN2 braids are also known as free braids or Gaussian braids or whatever. Actually, to draw these braids, I do the following. I take a motion of several points, and I can put classical crossings between them. For example, this is the first strand, this is the second, this is the third. When they do not really intersect, I put virtual crossings like that, and I use the red color for the third strand. So this is my picture, and here I have, for example, crossings between 1 and 2. Of course, this can be written as a virtual braid when I have some generators corresponding to the intersections between 1 and 2, and I have some generators for 2 and 3. For 1 and 3, I can write down the relations. But you see, let's look at these two generators, 1, 2, and 1, 2. I have these two generators between the first strand and the second strand. So eventually, it could happen that these two strands would form a bicone, and they could eventually cancel. But in this case, this is not the case. Why? Well, because for this concrete situation, when I look with, when I deal with such braids, I can count some very simple number modulo Z2. And for these two crossings, it will be different. Namely, let's do the following. Let's go from the top point of the first strand until the crossing, and from the top point of the second strand until the crossing. And let's count the number of intersections with the third strands. So here it will be 0. So this will be 0. And if I go from this to that crossing, and from this to that crossing, it will be 1. So here is the only crossing. So this is 0 and this is 1. And actually, one can easily check that the parity of that number remains the same if I apply, say, the third Reidemeister move. So, for example, if I had some number of crossings here, it can change by 2, but this number mod 2 remains the same. So here and here, they have the same parity. This means that whatever I do with this crossing, it will never get cancelled with that crossing. And actually this means that for those braids, if we put one more technical restriction, that the total number of intersections between 1 and 2 is even, 1 and 3 is even, and 2 and 3 is even, then we would get a homomorphism to the free product of Z2 and Z2. Why? Well, because if we have a 3-strand free braid, well, virtual braid, but I want to forget some information. Over-under information doesn't matter. Right-left doesn't matter. The only thing which does matter, which strands do intersect here. And then, whenever I need this crossing, which is even, I write down A. And whenever I need this crossing between 1 and 2, I write down B. And I have a word in A, B, and B, and B, A, B, and B. The only thing which can happen is that A cancels with A, or B cancels with B. But A will never become B. And this is a homomorphism to a free product of these two groups. Now, of course, you can see that if there are more than 3 strands, there will be much more than 2 generators, and these groups will be powerful enough, and we can get many estimates for the crossing number. Which crossing number? Well, actually, let's go further, and we will see some estimates for trisecants and so on. So these 2 crossings, similar to those ones, cannot be cancelled. Now I want to say that there is a non-theoretical counterpart of these braids. Actually, they are called free knots. They have different names. They first appeared in the paper by Turaev, something like 2004, as homotopy classes of Gauss words. We just take Gauss diagrams, modular moves, but for Gauss diagrams we forget everything. We forget over-under, and we forget right and left. We take abstract Gauss diagrams without arrows and signs, modular, formal Reidemeister moves. So we take 4 valence graphs with opposite edge structure at every vertex and do this. So initially they were conjectured to be trivial all, but they are very far from being trivial. And the reason that they are not trivial is that there are invariants which evaluate the diagram of itself. Well, now I'm not going to give a talk on free knots themselves. Well, I gave lots of, but in fact, for free knots, there are invariants which satisfy some very simple formula, very easy to remember. The formula sounds as follows. The bracket of k equals k. So this formula means that in the left-hand side, we have some object which is modulo some moves. Say 4 valence graph module moves. And in the right-hand side, I have just a graph by itself. So this means that the value of my invariant for a knot given by a graph K is the graph K itself. So what does it mean? This means that if my knot K is complicated enough, then I can take some knot K prime which is equivalent to K. And then, since my bracket is invariant, this means that the bracket of K prime is equal to the bracket of K and is equal to K itself. Note that in the left-hand side, K means some object modulo some moves. And in the right-hand side, K means just a graph itself. A particular graph obtained by some geometrical operations. And this geometrical operation means exactly that K will live inside any K prime is equivalent to it. So if we have an object which is complicated enough, then it will live inside any object complicated to it. I'm not going to give an exact definition, but this formula will appear in many situations when we have some virtual knot theory parity and so on. Now I want to get some information for such braids. Note that these braids are GN2 braids. Note that GN2 knots or free knots or homotopy classes of Gauss words already have very powerful and very variant pictures. And note also that classical braids have maps to GN3. Now I want to say something about classical braids and our work with Igor Nikolov. Actually, I will tell some words about calculations, but I don't want to have any technicalities. So, assume we have a free group. Again, we can get easy estimates for the number of letters needed to write a word. So, for example, here we have 7 generators. Well, because the number of letters in the reduced form is 7. But what can we do if we have an arbitrary group? Well, of course, in the arbitrary case, we cannot do so much. But if we have a map to a free product of some abelian groups, then we will have obvious estimates. Assume, for example, we have some group, and we have a map from a generator of this group to some generator of my group G and to some generator of the free group. Excuse me. Then, of course, the number of generators in the image will give the estimate from below for the number of estimates in the pre-image. And if I have, for example, my group GN3, then I can get a homomorphism from that to some free product of several copies of Z2. And each generator is mapped to a generator of that. And for the free group, the number of estimates is obvious. And then we can get an estimate from below for the number of triseconds, which is a very good complexity. And actually, with some more work, we can get some estimates for the unnoted number, because we can explicitly write down what happens if we perform the crossing change, what will happen with our words in GN3, and then we can rewrite it for free groups, and then we can get obvious estimates. And actually, here is some obvious example. So, for example, if we have a braid, braid on 4 strands, and if I want to rotate the first strand and go around this, the second point, I will get first the intersection 1 to 4, and then 1 to 3, and then 1 to 4, and then 1 to 3. And this is the first example of the image of the generator of a pure classical braid group. And then, of course, we can do the same, and this is explicitly done in my paper with Nico. Why have I written about GN4? Why 4, not only 3? Well, because this principle with dynamical systems and appropriate codimensions works for a generic situation when we have good codimensional constraints. Look, if we have points, we can look at those moments when they are on the same line. And then there can be 3 points lying on the same line. But we can also look at those moments when they lie on the same circle or a straight line. Then there can be 4 of them. And then we can write down 1, 2, 3, A, I, J, K, L. This is a more technical issue, but this gives me a homomorphism from the braid group, pure braid group to GN4, and this is also done in my paper with Nico. This is just to show that we can have different dimensions, and actually some other applications of that. Well, in fact, classical GN2, classical braids can be thought of as GN2 braids because we have a dynamical system of points on the line. We have certain points on the line which may go through each other, but if they go through each other and we want to have a braid, not just a permutation, we keep some over-under information. So here K is 2. Generically 2 points may coincide at some moment. So trisecants give rise to relations. This is exactly the description of GN2 braids. So classical arting presentation is something which I call GN2 presentation. But we can also have GN3, GN4, as I said. Actually, we can do the same for weaves, lines, and RP3. So we can also consider similar properties. I will skip something here. Also, we can do this for braids on the sphere. Also, we can do that for if we look at m-dimensional planes in, say, RPM plus 2 considered up to isotopy. Also, we just look at appropriate NK and at some properties in general positions. How many points, how many particles, in this case, particles are not just point, can be in the general position. And so here is the answer. So for example, for m equals 1, we can take k equals 3, and in general case, 1 takes this. And one can also get homomorphisms if we have a group to some g and k, and we will get invariants which are valued in g and k. We can also study some discriminant sets, Grassmannians, and many other things. And now I want to ask about knots. So what about knots and links? So if we have a braid, then the situation is very easy. The number of particles is the same. The number of points doesn't change. Points always go down. But we can look at a tangle. Well, in the case of a tangle, a point can go down and then up. You know, I'm really very sorry that I missed the trip to Peterhof, because we can really have more complicated dynamical systems. There is a very important structural difference between tangles and braids, because if we have a tangle and we look at its section by horizontal planes, the number of points can change when we get from one level to another level. And if the number changes, then we are not in the position of constructing GN2. And then we will have say GNK braids, but we will have some other objects. Some other objects like GNK tangles or GNK knots or something else. But we already know that GN2 knots are very much complicated and they possess very powerful invariant. You know, usually for braids life is very easy. Everything goes down and it never goes up. And we have just groups. And for example, the Kontsevich integral for braids can be written down as a single formula when we plug in something for crossings. And the same for my GN3 braids. But if we want to do something with knots, well, it will be more complicated because one has to draw more pictures, more moves, and more invariants. But still, already GN2 knots have very powerful picture invariants, so GN3 knots are more complicated. And now there may be some obvious questions you may ask me. For example, if this map from GN2 from the pure braid group to GN3 monomorphic. The answer is obviously no, because if we consider the center of the braid group, when we rotate all points and they remain on the same circle, then this rotation will have no moments when some 3 points are on the line. They are always on the circle, so this will go to the unit. And this is a kernel, but well, never mind. My map can be easily modified to some map from PBN to GN+1, 3, when I add some artificial strength, and from that I can recover Artin's representation, forward section, and get complete invariance and whatever else. So I will get a monomorphic map like this. Actually, word problems in various groups can be very often solved because there is some topology behind that. Because we can draw some pictures and actually just referring to that work we wrote with Alexander something like 15 years ago. Why can't this action of the braid group on the automorphism group be faithful? Because of the pictures. Because of the pictures. And pictures in some ways similar appear to solve various problems and various word problems for groups. And actually, GN2 have very nice presentations because they have some pictures. Possibly, I will skip some 2 slides. This is about the Yang-Baxter equation, so one can do some Yang-Baxter equations for the generalization of the Yang-Baxter equation for the case of GN3. Actually, the usual braid group is GN2 braid group, and we can take this, and one can do the following for any k, and one can get similar equations. Actually, I would like to conclude my talk with a couple of unsolved problems. So first of all, I don't know whether these groups, which contain classical braid groups and many other braid groups and have lots of automorphisms, whether they are linear. And of course, whether we can solve the word problem for them completely. We can solve the word problem for some groups related to them, but I don't know about them. Are they linear, and can one solve the word problem? And the second problem is not a problem, but possibly a suggestion. Well, take your favorite invariant of some topological space. Well, state some homology group or something which is expressed as a sum of numbers, units, whatever. And try to plug in pictures into that. So if your invariant is a group, try to put generators which first start from Z2 and then get to maps to GMK. So this is now a work is in progress with lots of collaborators on various subjects. And here is the main list of references. So here is the initial paper when I defined this right-master knot theory on the archive. And here is the very recent, just some days ago, paper with Igor Nikonov. And this is my old paper on parity when I disprove Turaev's conjecture and constructed lots of free nuts. So I think
Thank you very much. These questions, remarks, so if there are no questions,